Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Stand-up comedy act today for the last hour. So Roy Campbell is professor at the University of Illinois, Urbana-Champaign, someone I used to work with or had the opportunity to work with back when I was at University of Illinois. And he's going to be talking about his work on Gaia and how it relates to, or how it is, an advanced collaborative environment.
Thanks, Patrick. Patrick was one of the brilliant students at the U of I, and obviously Microsoft grabbed him as soon as he was ready to be able to work on his own. I want to talk about this whole issue of, well, actually it's sort of convergence, and I'll get around to that in a while. But I think we're sort of sitting there with lots and lots of interesting things happening, both in the collaborative environments, on the grid, in ubiquitous computing and so on. And because of various complications in, shall we say, the economics of the current state, we're unable to do anything about it. And it's kind of very frustrating. But what I see happening is very exciting, and this conference is very exciting too. There's lots of things that we could be doing. I'm going to talk about some, and probably make mistakes in spelling, but never mind. I'm going to talk about some of the work that my students have done. This is a project that I've been working on for about 5 years. It was funded by NSF, and it's sort of winding down now as I graduate all my students. But these were all PhD students, and they all did major parts of the work that I'm talking about. I'm going to concentrate mainly in the presentation on the work that we're doing now, which is being done by Shita, and some of the work that's just been finished by Anand. But I think it's difficult to give any talk without recognition of all these guys. So what I want to talk to you about is that collaborative environments are really sort of a great example of a more sort of interesting thing that's happening, which is that we're trying to make the world active, if you like, that we're trying to relate physical and computational environments together and make, whether it's a discussion, a collaborative discussion, it's education, it's actually designing something, it's whatever activity we're doing, we're trying to relate both the physical and the intellectual activities together, link them together so that there really is seamless. There's the things that people are doing physically are linked straight into the intellectual things that they're presenting. And to have that correlation going on, supported by computing environments. So I'm going to talk a bit about active worlds and demonstrating what you can do with active buildings. I'll show you a little bit about what we've managed to do with our pervasive environment. Now what I want to do is to go on from there and talk about a very difficult problem that we've got, which is that, in fact, what we're trying to do is to automate human activities. This is our sort of rightful, we're engineering, we're trying to support human activities. There are a lot of fundamental problems facing us in doing that, and some of these are what some of the students are trying to battle with now, but they'll make attempts on it, but I think these are very, very difficult problems that will last for a long while. One is on what the notion of a task is when humans are involved, and the other is what the notion of you build a collaborative environment, you get lots of computer tools together, but really it's a bunch of resources and you have to manage them. And the difficulty is when you don't really know what the tasks are, and when you keep changing the hardware and you keep changing the software, coming up with sort of ways to manage the resources that you put into some sort of collaborative environment becomes very difficult and very time consuming and very expensive. And perhaps one of the solutions, perhaps not, but one of the a possible solution would be to look at how we could sort of extract workflows with what people were doing and try to deduce from them how we should actually manage the resources. But that gets into a very, very large topic. Anyway, I'm going to talk about active worlds, and the whole notion is that you've got the spectrum of computational and communication devices you want to pull in, but they're all different. Right? Every single one is unique in sometimes totally different from everything else that's around. And what we're thinking about generally is this area of creativity, that humans want to be creative, they want to design things. Certainly if we are in the West, we want to stay ahead of the curve in production or in sort of our economics. We have to think about how we can automate all of the things that we're trying to do in being creative, and in particular that includes collaboration. And this really gives us a huge challenge to work on, and is not easy to sort of accomplish. Nevertheless, you could say it's the tail end, if you like, of the information revolution is now to start automating all sorts of tasks that we thought were difficult in the past. And the notion would be that we want to take the behavioral context of the users and somehow automate this, enhance it, so that we are much more productive in everything we do, whether it's science or any other activity. So what the main benefits we're going to get, and this is the benefits that you sort of keep hearing from every presentation, that we're going to take information, we're going to be translating information to and from sort of physical properties of the world and looking at them in our information environment and vice versa, be able to transform data and provide some sort of cooperative computational environment from embedding all these wonderful devices, obviously in a network, obviously to be used by humans. So we've got lots of environments, and I probably left off lots of environments, and I apologize, it's impossible to make a list. We have lots of different sorts of devices, and particularly the ones that are getting exciting are the things like wearable devices, cell phones, things that are in the infrastructure, embedded devices. And to some extent, you know, you could picture that table as just another embedded device. Nice, beautiful walls could be embedded devices. What we're doing more and more is to build these embedded devices into every piece of infrastructure around the planet, whether it's a bridge or a table or whatever. And we want to take advantage of them, but they're all different. And up to now, all we've got is sort of very limited scenarios, science labs, grocery stores, healthcare. But it's out of these things that one would hope one could grow a whole new set of exciting support for human activities. And if you're sort of an optimist, as sort of a lot of scientists are, what you'd hope is that we could establish sufficient support that we get widespread deployment and some sort of ubiquitous computing that would really sort of make this next 100 years take off and become radically different. But we've got a lot of challenges, and the main challenge is the complexity, particularly faced with trying to program all these things when they're very, if you like, they're not very well defined, some of the things that we're trying to do. And so we have great difficulty coming up with programs. The programs are littered with if statements and case statements. We have to keep changing the programs as the devices or as the software changes. It's very difficult to manage, very difficult to use. And so the whole complexity is tough. And of course, on top of that, we're faced with parallelism. If you really want to describe a collaborative work environment, it's a very parallel environment. There's all sorts of things going on. and we want to be able to describe these things, and we're not very good at describing parallel activities at all. The advantage is, I think, huge, and it's not obvious, certainly to our politicians, but it's not probably obvious to the general population what the advantages of what we're trying to do. And I'd like to just wave the flag a bit. What we're doing is extremely important. We're faced now with a world that's getting smaller and smaller because of the communication. We've sort of got the world is flat type of hypotheses. And all of our economics is based now on the fact that we do have this very fast communication between everywhere, and we have very good distribution schemes. And so this naturally lends itself to trying to automate human interactivity and human thought and human creativity, provide tools for them. And what you're effectively looking at is what are the tools for globalized economies. Right? And you want to sort of automate everything that you can possibly do to help users operate in that sort of environment. And the types of things that I think we're coming to face is that we're going to devise tools that will make us use our workforce incredibly efficiently, moving work around, moving users or the workforce around, changing the, we have these supply chains, we have these cooperative insourcing, outsourcing, whatever. We need to provide the computational environment to allow all this to happen. And this really sort of gets into the fabric of the, of ubiquity, if you like, of collaborative work, operations, of all those other sorts of things. And this is what's going to be the thing that makes our efforts really pay off in the long run. And of course, on the flip side of that, you not only increase the use of workforce, but you also increase the huge number of consumer services, for example, use of collaborative environments and things in the home. Well, the intuition that our project had was that you just don't have a bunch of isolated devices. What you have instead is a fabric, and you have to make that fabric out of something. And what it's looking at, what that fabric has embedded in it, is a lot of resources, and those resources have to be managed for all the different things that are going on. So it begins to look very, very much like some sort of distributed operating system. So the environment that we built was actually a distributed operating system. It's built out of distributed object system components. And those components could be anything, pretty much. They could be, DCOM components or whatever. It doesn't really matter. The infrastructure glues everything together, and it allows you to locate things, name things, authenticate things, authorize, create events, and provide context awareness and data. And if you've got that list, is pretty much all the types of services that you need in these types of environments. Be happy to consider some others, but those are the ones that really stand out that you have to provide in order to provide something along the line of a collaborative environment. The difficulty that we found in building these systems is that you actually have to make things programmable at multiple different levels. So there are levels at which you would like to describe human tasks. There's also levels at which you have to describe devices. And they're so far apart that you need different notations, and so on, in order to be able to accomplish that. And you also need to manage these resources, but fortunately we know a lot about management of resources, and so we can sort of borrow tremendously from OS-like behaviors, our algorithms, to do that. Now, what we're envisaging is sort of obviously building very, very complicated, or very large systems, and we need to develop tools to help us build those large systems, and one way is to make them autonomic. It's very easy to build a smart room or something, or a smart classroom, one-off. The trouble is you soon find yourself having to rework all the software in it because something changed, some usage changed. And trying to bring up some of these environments is very difficult. You know, it's bad enough just trying to boot my laptop sometimes, but trying to boot a whole room full of machines can be daunting. So we need to make all of these sort of processes that we normally sort of regard on an individual basis, because they're in collective entities, we have to sort of automate the whole thing and make them all much more autonomic if we're going to actually manage this. So with IBM's autonomic computing, they were sort of saying was self-configuring, self-optimizing, self-healing. And these things really do apply, especially in a ubiquitous computing environment, because of the quantity of machines and the difficulty of what you're trying to do. The other issue is that really you're trying to do task-based programming, and this requires you to step back and parameterize much, much more what types of systems you're building. And what you're going to hear in my talk is that what we built is a system that supplies parameters dynamically at runtime, and those parameters can be quite high level and quite abstract, but they can be automated. The environment itself, it takes care of lots of the low-level details, and particularly one of the things it has to do is to recover from phase. And that by sort of parameterizing this and using a task-based programming environment, you can at least get a handle on some of the complexity of building these systems. So what we built was a system that supported a notion of an active space, and you can see some happy active space users, from sort of PDAs and telephones up to big displays. The active space, the idea of that is it organizes the network devices into a distributed system, and then that distributed system cooperates and coordinates its activities with mobile users. And that this in turn automates human endeavors. So you can see some happy people doing different human endeavors there. We've looked at some of these issues much more in a sort of academic sense. I think it's time to look at some other more interesting commercial economic types of activities, but these are the ones we did look at, you know, sort of education and so on. We used all sorts of different machines. You can see location, you can see, well, this is a display of where people are in the building. You see all sorts of fancy devices, that's fine.
Is that a cell phone, or what is it?
Yeah, it's a cell phone. It's a bit squished, isn't it? But it's a cell phone, yeah. This is our location technology. It's a Ubisense device, and it tracks these little tags. No, they're big tags, actually. They should shrink as the technology improves. But it's using UWB sensing, so you get sort of 6-inch type of accuracy. Sometimes. Depends. When the weather's good. And then, yeah, well, there's lots of extra pictures in here, I suppose. But the notion of location awareness gives you a huge sense of what users are doing in the environment and of context. Now, you can do it in all sorts of ways, and I'd prefer to do it by video, but we're sort of clutching at our video technology didn't work very well with all those big displays, so the Ubisense technology is actually has been reasonable for what we've been doing. You can see the camera there sort of being directed by Ubisense, so it moves around and does things as people move around. And the idea is anyway to sort of empower the users in some way to do even more exciting things. Lots of blurb. We built this notion of active space. We could effectively apply it recursively to build buildings of active spaces, and so that's what we've been doing in our building. So the sort of activities that we've managed to do, sort of things like tours or exhibitions or seminars or lectures, we can somewhat support in between crashes. We've shown how we can sort of migrate, suspend, resume sessions, multiple different tasks, and actually migrate them from one place to the other. We built it all out of COTS, and we built some example collaborative environments. As I said, Gaia OS is sort of just generic. It's built out of Cobra, actually, but it doesn't really make... You could build it out of anything. It looks something like this. It's basically got a core at the bottom which implements remote distributed objects, and then on top of that there's a whole bunch of services, and then there's a sort of application layer for doing QoS and management and so on, and then the applications run on top of that. So it really is sort of just a straight object application. And the sort of things that we think we've contributed, one is, and we'll talk a little bit about how it does it. One is evolution, that really what you've got with humans is a sort of rapid prototyping environment, because humans always want more. As soon as you give them something, they want to develop other things. So what we did was to build Gaia to provide rapid prototyping, and we provided support for doing that, and so that's where the autonomic came in. We actually use ontologies to provide a mechanism, a handle for Gaia to be able to work with new devices that it's never met before, and that's kind of cool. And then it has an online semantic model based on these ontologies and associated logic, so it can reason about what's going on. It has some distributed coordination protocols. So, for example, it has an extended model view controller for dealing with multiple screens, for doing publish, subscribe, and sessions and so on, access control. And then it has an infrastructure for doing context-sensitive data and actions, as a model for doing that, and a model for reasoning about these actions and so on. So just for example, one of the things that we found difficult was to actually write scripts for managing multiple displays, doing various things. But it turned out that actually if we allowed sessions, and we allowed you to build these sessions out of pieces, then Gaia could keep track of it for us. So that's what we did. We have these sessions with multiple applications on them, running on different machines, on different displays, and then we can save and restore these sessions. And so we can now, from a save session, we can switch to a different save session. So we can change the nature of the room from, say, a seminar to a classroom or whatever, very quickly by switching these sessions. And that was kind of an interesting discovery. We could also migrate the sessions from one place to another. So you have a session with, lots of Office applications, and you can do a follow me into a different room and create them in exactly the same states where you left off in a different room, doing a sort of follow me type of environment. And at some point I'm supposed to show, oh yes, okay. So let's see what I can do about convincing you that this actually works. So here's got a little bit of video just to sort of illustrate some of these things, if I can get it to work. Oh, wait a minute. I bet there was some audio somewhere. No. Where did the audio go?
There you go.
Ah. Now we'll start her over. May not work, of course.
Extending the reach of traditional computing systems
So this is,
to encompass the device.
everyone's got to have their avatar, right?
Hello. I am Gaia, the software infrastructure that supports the construction of active spaces. By extending the reach of traditional computing systems to encompass the devices and physical space surrounding the machines, entities both physical and virtual may be allowed to
I don't know where she got the
seamlessly
blue
interact.
hair from.
Physical spaces
But-
become active spaces. I bring the functionality of an operating system to physical spaces. In this demo, my assistant Hercules and I will demonstrate location awareness and mobile device support in active spaces.
To enable location-aware applications, we employ UViSense location technology. UViSense represents a new class of sensing devices that are economic to deploy in a building and have an accuracy of 6 inches 95% of the time.
UViSense is based
So this
on
is all
ultra-wideband
synthesized.
technology
These are
operating in the
AT&T
2.7
synthesis
frequency
algorithms,
range and uses time-of-flight WWB packets.
And the whole thing's run off
Less
of
prone to errors from
a distributed
hash patterns
script.
of a short wavelength.
In deployment, it uses sensors, like the one shown here, placed on a 10 or more meter grid, making the system reasonably economic to deploy. UViSense provides a simulated 2D and
So
3D
UVis-
visualization.
UViSense
and simple
is supposed to
triggers
be,
based on volumes.
The UViSense tag transmits UWB packets. The tag has two programmable LED displays and two programmable buttons. The tag shown here is a prototype.
So this is a replacement
The
for
production version is expected
the
to be
audio
much smaller.
that they were using at the AT&T Cambridge labs.
By integrating UViSense location technology into the Gaia infrastructure, it is possible to create rich location-aware ubiquitous applications and services, as we will demonstrate in this demo video.
We will demonstrate location awareness and mobile device support by considering a seminar scenario. Assume that Bob is scheduled to give a seminar in an active space.
Using his mobile phone, Bob is able to interact with Gaia and find out the location of people and objects. He is also able to get a list of people
So
and
that's
resources
actually
that
a
reside in a particular
Projection
room.
of what the UViSense is detecting in the room.
When Bob enters the active space, Gaia detects his presence and customizes the space and resources according to his preferences and according to the schedule set for that particular day, time, and activity.
So what the
Bob
well-dressed-
is carrying his UViSense tag in his pocket.
We're not very good
When Bob
actors.
is physically close to the designated display, Gaia automatically launches the necessary applications and files that Bob will use for his presentation.
To make it easier to stream this presentation over the web, a webcam is configured to track Bob as he moves around in the room while giving the
It'd be much nicer to use video
This
to track
provides
him, but
remote users with a real-time video
we found a lot of
stream the
interference
vision
from the
without
displays
need
at the
for a
back.
cameraman.
The tracking mechanism here does not use vision, instead it tracks the UViSense tag that Bob is wearing. This provides better level of privacy, as Bob can choose to put down the tag if he wants the camera to stop tracking him.
Sue, for example, decides to watch the seminar remotely over the web. Note how the camera automatically tracks Bob as he moves around. Moreover, if Bob decides to leave the room, the web interface can switch dynamically to the feed from the nearest camera to Bob.
we've actually used it to track people from one room to another room, and that works quite well.
By
They have
capturing
multiple
accurate
cells you
real-time
can link
location
together.
information, it is possible to build applications and services that follow users wherever they go. Gaia provides primitives that allow the different components of an application to run in a
So this
distributed
is
fashion.
these screens are completely working on different machines,
Of
but
the presentation application follows
you can
Bob
move the
to whichever
controls around
display
between
Bob
them.
is nearest to.
now you can even have the controls sort of do a follow me.
Bob now moves to a third display, and the controller follows him to this display.
Now don't ask me why they.
An
This
audience
was the
member
students
can leave
made
the
this
room, but
piece of
still
the
be able to
video.
follow the presentation through his or her PDA device. For example, Bob decides to leave the space.
By using his PDA device, Jalal is able to watch the current slideshow and add his private annotations to the slide. The slideshow here is synchronized with Bob's slideshow. So when Bob moves to the next slide, the correct slide will appear on the PDA.
Now Bob wants to conduct a poll. The Gaia proxy service allows the poll application to run on different mobile devices that have different resolutions and use different networks.
I don't know what it is either.
One student is answering the poll using her mobile phone service. The other student is using his PDA device with Wi-Fi. Results are then received by Bob in real time.
So, I mean, it's just a sort of an example of what you, some of the rich environment you can do there. Another student came in. Oh, I see. I'm still running that one. I'm going to have to do that, aren't I? But another student came in, Mark, and he took the framework that we created, and we're working with Clara on a multimedia framework as well. And within a short time, like 4 or 5 months, this is what he'd managed to accomplish with it in the multimedia sort of arrangement. And I think this is sort of indicative of once you get a framework, you can actually build all sorts of very fast, interesting.
In the Gaia project, we are exploring the creation of distributed multimedia content in ubiquitous computing environments. By combining several devices and applications, we create a new modality of multimedia presentations which includes single-user applications such as PowerPoint, Windows Media Player, and Internet Explorer. The replication of applications in groups can easily augment presentations by duplicating content in multiple displays. In this room, we can see a presentation composed of 2 groups of applications. In one group, a video is reproduced in 2 different machines. In the second group, a PowerPoint presentation shows slides with information about the video being played. Mark can follow the presentation from his office.
This is a student that did it.
Note how the video playback at Mark's office is synchronized with the other room.
So this is using Clara's QoS framework. But now what we can do is use the model view controller framework and our support to get a much more rich environment, much richer environment.
Mark decides to join the room to interact with his colleagues.
So we have this notion you can bring laptops into an active space and they join into this distributed environment.
Note that the video on the laptop is synchronized with the one in the room. By changing the playback position in a certain video player, Mark can move back and forth in the presentation. All players will be synchronized accordingly. The whole presentation is described and controlled through a multimedia document that describes machines, groups of applications, and application members. By allowing generic description of machines, the document is capable of describing the presentation without making it room-specific.
So you have a sort of way of describing a very complicated multimedia presentation. And it's all using the same sort of framework, which is rather cool. So, oh well, that didn't work, did it? Wherever we are. Not doing this very well. Where are we? Okay, so when you look at all that sort of stuff, the problem we came up with was all the scripts are very complicated and they got lots of if statements in. And it takes a long while to debug the scripts. And then if machines are down, if one of the one of the machines in the room's down, then the whole thing breaks, right? If somebody reconfigures one of the machines, you've got a big problem. So, and then another question is, okay, supposing you want to take that, well, like the multimedia show, and you want to stop it, suspend it, like one of those sessions that we've got, and reactivate it in a different room, right? Should be able to do that, but how easy is it to program that? You've got all these devices that are very specific. So we wanted to automate this, and you'll see our sort of attempts at doing that, or at least how we approach doing this. So what I really want to talk to you about today is, this is what we've been doing most recently and into the future, is trying to make these spaces more programmable and looking at policies to manage the resources. Okay, so supposing you've got this video, Darth Vader, whatever it is, and the student that has got this walks into your nice presentation of, Beethoven's lifetime or whatever. How do you get the resources to actually sort of sort themselves out? How do you manage the resources in one space with these multiple sort of conflicting things going on? We actually ran into all sorts of problems with the location awareness system, because as you move from room to room, the location triggers things. Unfortunately, location can be a bit sort of not very sensitive to where you are, and also people tend to sort of unfortunately dodge backwards and forwards, and so you get the whole system sort of oscillating as somebody sort of moves backwards and forwards at a doorway, right? And it just allows the whole thing to fall apart. The whole question is, how do you arrange policies so the rooms can actually remain stable and manage what they're doing? How do you resolve conflicts of interest when there's multiple people wanting to do the same thing in a room? And how do you sort of arrange between rooms? Supposing I've got tours in the building, and I've got a whole bunch of people being presented, the Siebel Center, and they go from room to room. Can I actually sort of schedule them through the rooms so that they see the same things, but perhaps in a different order, so that the groups don't collide, and do all this in real time? Right? You would like to program everything clearly, and you would like to understand what's going on. So, on the programmability side, the difficult issue is that the applications keep evolving. You have lots of different applications as well. The environment that they're running in with all these devices, unfortunately, if you have a room with like 50 devices in, especially PDAs, they change all the time. Every day they change practically, because the lifetime of a PDA is about 2 years. So you're always seeing new things coming out. And then Microsoft is always giving us lots of additional services to run in this environment, which is fine, and it's a great benefit, but the system doesn't know about those services. So you would like to add them into what you can do in this system, but you'd like to add them in dynamically. And then you also have different sorts of human behavior. You would actually like to keep prototyping, keep on enhancing the environments, the tasks that you manage in these environments. So you might have, a distributed discussion with Argon, say, but it's going to evolve, otherwise it's probably not going to be used very long. And how do you actually allow that environment, those tasks and everything else going on in that environment, to evolve in those circumstances? And the answer that we sort of came up with is by programming things at much higher levels. What you would like is, if you like, very high-level parameterized tasks, where even what the task is may be parameterized, and you want to fill that in from the context within which the task is actually occurring. So you want to take advantage of polymorphism, but you want to provide as a parameter that polymorphism context, right? This sort of ongoing gathering of information that everybody talks about in these ubiquitous environments. But then how do you make sense of it? Now the difficulty is you've got tasks that you would like to migrate from place to place. You have lots of different groups wanting to use your system and involving different ways that the humans should use it. You have all these devices changing. So you need a language within which to talk about all of this and which to program all of this. So what we did was to fall back on the semantic web. And we were looking around for what technology would actually help. And so what we did was to adopt the notion of ontologies and its use in the semantic web. What we decided to do was to allow people to build their own ontologies. If they're having their own environment, their own set of tasks they're trying to create, allow them to build their own ontologies. And then we would match those ontologies together using some of the algorithms from the semantic web in order to be able to understand what those ontologies meant, right? So we take a small ontology from here and a small ontology from here and try and match it against what we know to build an understanding of what those things meant. And then we would implement that at runtime. So this is what Anand Raghunathan built as part of his PhD. So you have a task, which is a set of actions. So you could think of it as a workflow, and it's performed collaboratively by a whole bunch of humans. Could be things like displaying slideshows or whatever. You have task programs written at very high level. They're going to run in all sorts of different environments. You want to be able to use existing languages. Lua is a sort of scripting language that's based on C++. So we allow you to do that, but everything's polymorphic. The parameters are supplied at runtime, and the notion of what the parameters are is resolved using these ontologies. So the end result is that we get lots of reusable activities and subtasks that can be recombined in lots of different manners. Now the parameters fall into three categories. You get parameter obtaining, state gathering, and world altering. And these are resolved in different manners. So the parameter obtaining are gathered from the end user, or they're inferred from the environment. State gathering are queries. They query services or databases which tell you what's in the room or what's in the environment. And they're world altering. This is where they change the state of the environment, creating or configuring things or moving and destroying items. They look something like this. Parameter obtaining usually end up asking the end user or using the discovery service. There's state gathering, and this is based off a programming model we've got. It examines the current context and state services that are in the environment. And then there's world-altering activities, and they usually invoke methods to change the state, which means doing things to devices and services. So, for example, if you have a presentation task, there's different ways of configuring the room, different displays, controllers, lights, speakers, shades. That would all be taken care of through that first exploring the room part of that way of handling the parameters. Sorry. There's security policies that they get dealt with in the same way, and failures will be, well, you go to the room and you find out what's actually working in the room, and you configure your system according to what you found working there and what the descriptions of things in the room that are working will do for you. So let me, let's see. So in this paper, the PERCON paper 2005, what we described is sort of high-level operands and operators that would do this. Now, what sort of criticism we got of this were that it wouldn't allow a great deal of flexibility in the room responding if there were conflicts or other things to the actual programming model. So Shitan's been working on that as the next step in our project. But essentially in this programming model, we've got operators for querying and changing the state of the operands and relationships to the operands. So you can start, stop, move applications. You have operands and operators which were based off these ontological hierarchies. So they can be changed, basically. The hierarchies are, how you could say, are sort of very time-limited. They can change over time very easily. And you integrate these hierarchies together in a sort of configuration moment of the room, but then the applications can exploit them, and this way you can bring the room up to date with what the latest situation is with availability of hardware or software or whatever. So getting down to it, the notion is that you take all this domain knowledge about how the things are organized, you define hierarchies to describe them, and then you write policies and constraints using these things, and these get checked at different times when you're actually building the room, when you turn the room on, when you actually run an application, depending upon what the nature of them would be. So, for example, here, this is saying that you require some sort of PowerPoint viewer device, and it could be anything of these type of varieties. Now, these things would be mentioned in your ontologies, and what corresponds to a laptop could change. So we did the devices are a sort of a classic example of describing them using ontologies. This is the ontology used for the device hierarchy in Gaia. And this will be an example of one of the scripts used in the Olympus to actually configure a slideshow. And as you can see, it's quite sort of devoid of what's going on or what particular device is being used or even what slideshow application is being used. Those are all resolved by going off and looking, trying to match the ontologies against what's in the repositories and so on, and filling in the details as it's running. All right, so this is all sort of dynamic script being created as it runs. Fortunately, you've got lots of time to do that because humans are very slow. So if you have a slideshow, this would be the sort of flow chart through a slideshow task that will be created. It'll go and obtain parameters. It'll go to check to see if there's a slideshow running. Which you can see doesn't say what sort of slideshow application would be running. Anything which was classified as a slideshow application would count, which is where you'll come into your ontologies. Okay, then if there is, you attain what's left of whatever systems are around. You reconfigure your existing application to use them and go off and do things. Otherwise, no, you do something different here. I'm not going to try and interpret the thing right on the fly. He also, this is an and again, he also created a widget that you could actually sort of constructively build an application that would run on what was in the room. And it would go off and do all the exploration and fill in the blanks, basically. We tried planning, and planning didn't actually work very well. But this sort of ontology approach did work in a reasonable time frame for i.e. people actually would stand for doing this stuff. I think it actually goes off and fills in the blanks, but I'm not too worried about that. All right, so what your notion was is that you would write tasks, you would write task parameters, everything will be in XML. There'll be a task execution service that generates task control GUI there, which you saw earlier on, and then it would go off and find out from the system through the discovery service what was actually around. We'd use Prolog for a lot of the reasoning. It would go and inquire on the ontology service to get any properties that it needs and use those to query the discovery service for the properties that it's got, and then construct the actual executable version of the script. So it used a lot of different technology in doing that. I'm not going to read that out. Well, that was great, but it didn't account for all of the different problems that you might have with all the resources in the system. So Sheetan's looking at policy-based management to remedy that. The notion is that what we wanted to build was a way to rapidly prototype building resource management inside a particular environment, active space. And we looked at different things to use. One of them is sort of event condition action rules. And they would look like this. If somebody enters a room, you would start up an application after authorizing that they can actually do it. If the active space is empty, you would suspend the space. So this would occur when person left, the count of people in the room 0, and so on. So a typical policy would be a set of rules in this, and the rules would all be consistent, one would hope. And what you would do is to apply the rules to see whether the actual activity can occur, or if that particular action can occur. But there are all sorts of problems with ECA-based management systems. It wasn't quite powerful enough. So, for example, we couldn't detect conflicts, different actions. If somebody, well, I was trying to think of an example. I'm not sure I can think of an example there, but basically you can get conflicts where you both believe somebody's entering the room and somebody's leaving the room because of what's going on in the room. And this is not nice. It's not very nice, and you can't resolve it very easily with just the straight ECA rules. So another example would be where you've got termination occurring, reasoning about termination with the rules. Another example would be verifying successful completion of the system. So what we did instead was to use an extended version of that. We actually sort of used axioms based on pre and post conditions instead. And then that allowed us to reason about all of the different things that we wanted to reason about in the system. So it could actually resolve some of the conflicts we were having trouble with. It involves sort of static and dynamic analysis. Anyway, I'm going to skip through that because I don't want to take too much time. But the notion was that in order to manage these rules and to be able to create dynamic management systems, what we needed was something which seemed easier to couch as a rule-based system. That may not be true in on all types of systems, but at least in what we were doing, it seemed easier to do that way, because you could just add rules until it kind of worked, and then you could refine the rules, and these rules will be interpreted dynamically. We still ran into some problems. Multiple rules are triggered by a single change. What sort of execution order do you have? What we're currently trying is to look at a sort of Petronet description of workflows inside the system and apply the rules from those workflows in order to resolve the difficulties we've got. And so his building basically, well, this is an example, an adaptation policy for monitoring what's going on inside the system, and he's got a set of rules here for saying what he should do in different circumstances with different machines. And I'm not going to try and go over it, but it's just what I want to give you is some of the flavor of some of the problems that we were getting. So this Petri now, we sort of workflow system, we sort of automated with some generators and other things to plug it in. Again, we had this notion that what we would do is to compile things as we learned about them into the system, and then at runtime we use that knowledge in order to query what's actually in the room and what's actually running. So you've got a sort of two-stage type of environment. And this is the sort of, you can see it's kind of getting a bit complicated, which worries me a little bit. And this is sort of the rules for policy enforcement. And it uses sort of all sorts of interesting things. Again, most of this is done at sort of in a sort of static way, and then you try and just at runtime use a minimum sort of amount to actually dynamically manage it. Anyway, he's used this system to do configuration management and to do some fault management. If particular devices break, to replace them with other devices that can do the same sort of thing, or if software is not available, to replace software with other sorts of software that would do the same task, and then do the conversion. So there's a lot of work in this area, not necessarily driven by trying to do the things that we were doing, but nevertheless it's out there. There's a policy description language in Bell Labs. There's policy management that's around in IBM research, which is doing some of the things that we were trying to do with the language. There's a Ponder project from Imperial. There's policy conflict detection research by Jane Kamiki, etc. There's declarative and imperative rule specification research, quite considerable amount. So we're trying to build on those things to enhance our environment. So what I wanted to conclude with was what seems kind of a nice, simple sort of, I suppose 4 years ago, 5 years ago when we first started, a lot of these things seem very, well, actually a lot of these problems seem very academic because we couldn't actually get anything to work. What we had to do was to solve each of these problems in turn through the 5 years, and I'm sure that's the same with each of the collaborative environment experiments. It's very difficult to design, plan, and build the system, get it right, and then use it continuously thereafter. What we effectively built was a prototyping system, and we kept on adding to this prototyping system. And we were lucky, I suppose, because we built it as a prototyping system. In the first place, we built it using sort of off-the-shelf technologies that we could use to do prototyping. We used a lot of dynamic binding and so on. For example, when we use COBOL, we're using a lot of the dynamic invocation rather than compiled invocation. We're using a lot of scripting because basically you have to change these things as we sort of move along. But when you get to, well, after 5 years' experience, what seems obvious now is that these things will continue to change, and it will continue to be a dynamic environment. It's going to continue to be sort of needed to prototype everything, because you keep getting new things, you keep getting new applications, and this is not something that's, once you said, well, I want a PowerPoint demonstration, you think, oh, well, is that it? But then people add multimedia frameworks and video and everything else, which is all synchronized, so you can wander backwards and forwards for this video, and what you had before didn't work. So you really need to think of these collaborative environments, I think, as really sort of prototyping environments that you keep building on. And you need to think about what tools you can make to make the binding flexible enough that you can do that. And one of the advantages, it's not a sales job exactly, because there's other problems with ontologies, but one advantage with using the ontologies and describing these things using semantic web type of capabilities is you can keep extending it and changing it as you go, which is a big plus. One of the advantages of using things like Prolog in context reasoning is because you can go and change it very easily. I don't think there's a sort of a holy grail necessarily, but I do think you want to avoid early binding in building these systems. And then last, I would say, what did amaze me was the way that companies like the OMG, Microsoft, and so on have actually helped tremendously build these systems. Because if you look at them in the right way, they're just a sort of toolbox of objects that you can send methods to. And so you can start building these very these very sophisticated environments. Let's not say complicated. But you can start building these things, and it's because they've built them in these nice modular ways for other reasons. But this stuff is there now to exploit. So, questions? Want to answer some questions about?
On a regular PC, there's this dynamic environment of being able to plug in different apparatus and detect things that might connect to it, and the host server for that is what I would consider my central device, and then it's the one looking about. And it looked like from your presentation that the room was sort of the host.
In this, yeah.
Is that always the case, or did you also look at sort of the ad hoc nature of people here in this room decide that we're going to put something together, or we want to pick up components from the room and move them to other rooms? What happens?
Well, you can do that in our system, but it's organized around. There's actually a discovery service inside the room that understands what's been recognized, and it keeps a sort of heartbeat for what is actually it thinks is working, because things turn off at the most, the drop of a hat, especially PDA devices. So you have to keep all this apparatus around to be able to do that. And then when things move from another room from one room to another, you don't necessarily get events that they've done that. They may just never talk to you again.
Sure.
So
what I mean is, so your rule-based things like,
right.
If there's no one in the room, or I leave the room in the projection stream, if I, that's sort of based on a definition of the room being the holder.
Right.
Of that, right?
Yeah, and to a large extent, we were dividing the world up into entities, and the room is an entity, right, which you could either be in or you could not be in. Yes, it's kind of you're going to have to end up choosing some sort of domains for what's occurring.
Yeah. I mean, the reason it's sort of interesting is a lot of meetings like this. So if you took, as an example, you have a room CS 201, and you take all the students and their plasma screens and all their devices, and you have the room next door, CS 204.
You should be able to do it.
Yeah. So which policy is
that sort of? Well, we were thinking about that, and what you'd actually like to do is to sort of construct ad hoc rooms.
Yeah.
And you could see how to do that, sort of. Now, we actually haven't really done that. I mean, basically, you'd have to decide who does what inside the room out of all the pieces that you've got. And if we rearranged to rewrote our protocols and so on, you could probably figure out how to do that, but we haven't done it. Maybe it would be a good idea to start out with that premise rather than start out from our premise and move towards the ad hoc. I'm not sure. The other issue about it is that there ought to be better ways to have interconnections between different components without having to go through sort of symbolic strings and matching things and so on. And some of the peer-to-peer stuff would seem to be the way to go, that you could actually make interfaces based off some of those hashing techniques and so on, and make the interfaces much, much more flexible and dynamic without incurring, without actually having to invent anything actually, which would be rather cool. So there's lots of things you can do now that you couldn't do 5 years ago. Yes?
I think the task ontology type approach that you mentioned, I think is really important for a lot of things we do, in the sense that in understanding what somebody's trying to accomplish for any type of collaborative environment, you need to understand what they're trying to do and how to map that to the environment they're in. Kind of what Eric was doing for his room is they designed their room for a specific task. And understanding that task, and then they can map that onto the technology.
Right.
You've got an ontology that describes the task, and hopefully with all of the rules,
You can do some...
You can describe what Eric builds.
Yeah, well, certainly for limited things we can do that. I wouldn't say we can do that for everything.
But I think that's an interesting approach.
Well, I have this vision in my head, which is that what I would really like to do is get rid of all the hardware. Right? What I would like to think of is what the users are doing or what the users want to do, and then have that automatically generate the right implementations wherever I am. And the hardware is just sort of incidental. But the trouble is we've got a long gap to get there.
Other question. Did you find that the position detection really mattered to the level that the hardware gave you, this 6-inch, or really?
No. Well, it didn't really do that either.
Room, right? Is that
Yeah,
all you need?
the trouble is 6 inches isn't good enough for everything that you want. Lots of things you want to do. You heard all about, sort of playing games on the... Well, it's not going to handle that. And that's the sort of level of precision you'd really like to have. Location sensitivity in some senses. You'd like just one system in the room, right? But you don't have it. You have ultimately what you end up with is sort of like 10 or 15 different location systems. You've got, RFID badges. You've got the fact that somebody's touching a keyboard, the fact that somebody's in front of a video camera, the fact that they're wearing this badge or whatever. All these different mechanisms all have to come together, and so you need some sort of location sensing system that fuses all lots of data together to give you that information, which is a big pain. Right? It's not at all as easy as I would like. And the UberSense being accurate to 6 inches is kind of incidental, because that really didn't help you that much. I mean, it could have been a foot or 2 feet, 3 feet. I mean, it'd still be reasonable for the purposes we were using it, yeah. We were thought originally, you could actually use these UberSense tags like mice. They didn't work that way.
What's their commercial app for
Well, their big sales is to the military. They have a version of the tag. These tags work up to 90 meters, right? Well, if you take the limitation of the power, they'll work up to a mile and a half. So they're actually using it for combat training and stuff, for which it's reasonable.
I have a question.
Yeah?
I'm not sure I can frame it exactly right, but when earlier in the talk you had the picture of the ontology of the devices.
Right.
And the next slide you showed a function definition, and you said, okay, you got yourself a slideshow app, quote.
Right.
You got, here's some stuff, and you were describing that was a very, that the entries in that function call were not knowledgeable about the details of what was going on in the room. That those things got sort of picked up and sort of the quote definition of the slideshow thing was somehow figured out somewhere else. What occurred to me then was whether or not there was the potential for sort of accidentally mixing up concerns at that level, making it so that you had 4 or 5 things you had to do to sort of set up or initialize or whatever it was you were doing. And each one of those you had to, quote, put some stuff in. But if you didn't, it wasn't clear how much you had to know about what it was you were trying to do and the details of the properties of slideshow to know whether or not the next thing was a legal thing or a required thing or had special requirements that you had to, limitations on how you could do it, and I wasn't sure whether or not you could split that out in a way that was clean, so that if I went and said, let me make a subclass of slideshow that involves something else, LEDs or something else, that wouldn't cause everybody else downstream to get all messed up because there was some detail that you had to set up in some funny way.
Well, the way that this was written, yeah, that's, I mean, there weren't rules forcing the hierarchy, the subclassing, except for what the ontology mechanisms would do. So if there was things that were said outside of the ontologies, you would get into trouble for sure, right? The ontologies help you a bit, but it's not, it's not clear how far you can push all that stuff to what sort of level before it becomes intractable. Because those things operate very, very, I mean, if you try and resolve with the ontologies, it works very, very slowly. So you're going to have to do that. You can't do this sort of online.
So you have to put the care into making the ontology right, or in that function definition, or you put the care to make sure you don't trip something that's not supposed to happen.
Well, the answer is you're going to have to do both. You're going to have to do both, yeah. It's not very, I think at the moment it's not terribly, it's better than what we had before. It's not user. The thing is, we want to get rid of all the if statements, right? Because it was incredible, those conditional statements, we kept making mistakes on them. This thing at least does that, but it doesn't make too many guarantees. You can detect some problems with the ontologies, but if there's anything outside of that, it's tough to get. And if you miss out something on the requirements, then there's no way to reason about that stuff right now. Which is, it'll keep us all busy for a while. That's, I mean, the state machine stuff with the reason for doing that is because you can analyze it at least. Yeah. Well, thank you.
So the bus is taking off promptly at 5:30.